In this video, I'm going to show you how to do number 97 and 99 from Chapter 3 homework. Number 97 says combustion analysis of a hydrocarbon produces 33.01 grams of carbon dioxide and 13.51 grams of water. Calculate the empirical formula of the hydrocarbon. So there's quite a few important pieces of information. Our goal is to find the empirical formula. And it is a hydrocarbon, which means that there is no oxygen. If you're given a hydrocarbon, unless it specifically states that there's oxygen in it, assume that there's no oxygen. This is a combustion analysis, which combustion automatically means that we are reacting something with oxygen. So that's why in our results we have this oxygen. So basically we are taking our hydrocarbon, which I'm just going to put HXCY because we do not know how many hydrogens and how many carbons we have. And we are reacting it with oxygen. And this is a combustion reaction, and it produces carbon dioxide and water. Okay, so this is the data we collect. So we have this data, and this is our unknown. We want to figure out our empirical formula for the hydrocarbon. So the first thing we need to do is I want you to notice that 33.1 grams of carbon dioxide, that is the only spot where carbon comes in our reaction. So all of our carbon must be contained in the 33.01 grams. So let's figure out how much carbon we have. So if we have 33.01 grams of carbon dioxide, okay, we know that we have 12.01 grams of carbon for every 44.01 grams of carbon dioxide. So 44.01 is the total molar mass of carbon dioxide, and then we have our mass of carbon, and there's one carbon oxygen for every molecule of carbon dioxide. So we're going to have 12.01 grams of carbon for every 44.01 grams of carbon dioxide. And so then we're going to do the same thing with water. Notice that the only spot that hydrogen shows up in our products is in H2O, which means all of our hydrogen is contained in the 13.51 grams of water. So if we have 13.51 grams of H2O, now I want you to notice we have 2 atoms of hydrogen for every 1 molecule of water. Okay, which means we have 2 times the molar mass of hydrogen for every molar mass of water. So after doing the math, please notice which units cancel out and which units will be left with. You should get about 9 grams of carbon and 1.5 grams of hydrogen. Our goal is to find, again, the empirical formula. So that means that we need to find our mole ratio between carbon and hydrogen. So we're going to take our grams of carbon and we're going to convert it into moles of carbon. So for every mole of carbon, there's 12.01 grams of carbon, and that's directly from the periodic table. And for every mole of hydrogen, there is 1.008 grams of hydrogen. After doing the math, we should get about 0.75 moles of carbon and 1.5 moles of hydrogen. We need to find the whole number ratio, so we're going to divide both by our lowest number of moles, which is our moles of carbon, which gives us about 1 mole of carbon for every 2 moles of hydrogen. Therefore, our empirical formula is CH2. For every 1 mole of carbon, there's going to be 2 moles of hydrogen. Now I'm going to do question number 99. 99 is very, very similar. We are still trying to find the empirical formula. The only difference is butyric acid is a compound containing carbon, hydrogen, and oxygen. We're told that combustion analysis of a 4.3 gram sample of butyric acid produces 8.59 grams carbon dioxide and 3.52 grams of water. So let's see what reaction is actually occurring. So we have CX, HY, and OZ. Okay, we're going to try and figure out X, Y, and Z. That's going to be the empirical formula for butyric acid. And it's a combustion reaction, so we're reacting it with oxygen. And again, combustion reaction, so we produce carbon dioxide and water. Okay, so in this case, oxygen shows up in every single compound. So we're going to have to determine the mass of the oxygen in our butyric acid after determining the mass of the carbon and hydrogen. So we're told that the total mass of this sample is 4.30 grams. The total mass of the carbon dioxide is 8.59 grams, and the total mass of water is 3.52 grams. So what we're going to do is we're going to figure out just the mass of carbon based on the mass of the carbon dioxide. Then we're going to figure out just the mass of hydrogen based on the mass of water. And then based on the total mass of the butyric acid, if we have the mass of carbon and the mass of hydrogen, we can then figure out the mass of oxygen. So what I've done here is I've taken the mass of carbon dioxide given, and I have converted it into just the grams of carbon based on the relationship I know about carbon dioxide. So for every 44.01 grams of carbon dioxide, that's the molar mass of carbon dioxide, there's one mole of carbon, which means that there's 12.01 grams of carbon. And the same thing goes with the water, except there are 2 moles of hydrogen for every 1 mole of water. So that's why I multiplied the mass of hydrogen by 2. Okay, so now we have the mass of carbon and we have the mass of hydrogen, and we know that the total mass of our butyric acid is 4.30. So pause the video and figure out the mass of just the oxygen. After subtracting out the carbon and hydrogen, hopefully you got that in our butyric acid, we're going to have 1.57 grams of oxygen. So now we have the mass of carbon that's in the butyric acid sample, we have the mass of hydrogen, and we have the mass of oxygen. So now we need to figure out the empirical formula. Again, the empirical formula is the mole ratio between the carbon, the hydrogen, and the oxygen. So the first thing we need to do is convert all of our grams into moles. Once we establish how many moles of each compound we have, or each element we have, we need to determine the ratio. So we're going to divide by the smallest number, which is our oxygen. So we're dividing by the moles of oxygen. And if these don't equal perfect whole numbers, for instance, when I divided the carbon, I actually got 1.98777. 1.98777 is super close to 2, so it's fine to round. So I should have 2 moles of carbon for every 4 moles of hydrogen for every 1 mole of oxygen. So now we have determined our answer. The empirical formula for butyric acid should be C2H4O. So that is our answer. That's butyric acid.